Hello everyone, it is Group B1. Our group member is Wang Jiahui, Hakata Brahmana, Pei Xiyuan, Wu Hongkun, and Wang Chu. Today we will talk about eigenvalues and eigenvectors.
Eigenvalues and eigenvector. If A is a matrix, then a non-zero vector x or n is called an eigenvector of A if Ax is a scalar multiple of x. That is, if Ax equal to lambda x for some scalar x. The scalar lambda is called an eigenvalue of A, and x is said to be an eigenvector of A corresponding to lambda. So here's an example of eigenvalues and eigenvector. Show that x12 is an eigenvector of A is a matrix which consists of 3, 0, 8, and -1, corresponding to the eigenvalue lambda equal to 3. So as we see before, that Ax is equal to lambda x. So Ax equals to 3, 0, 8, -1 times by 1, 2, which is a matrix 2 by 2 multiplied by matrix 2 by 1. So the outcome will be matrix 2 by 1, which is 3 and 6, and the outcome will be 3, 1, and 2, which is a lambda x.
Now we talk about the characteristic equation. To find eigenvalues, we rearrange the equation A multiple x equal to lambda multiple x into the form the bracket in A minus lambda multiple I bracket and multiple x equal to 0. For this equation to have a non-zero solution, the matrix A minus lambda multiple I must be a singular, which means it doesn't have an inverse. That leads us to the characteristic equation. Define as determinant A multiple A minus lambda multiple I equal to 0. So this determinant gives us a phenomenon in lambda called the characteristic phenomenon. The rules of this phenomenon are the eigenvalues of A. Now we talk about an example. Now let's see the simple example. Consider matrix A is equal to 3, 0, and 8, 1. First, we compute the determinant of 8 minus lambda multiple I, which is the bracket 3 minus lambda multiple the bracket 1 minus lambda. So when this equation equal to 0, it can give us two eigenvalues. One lambda is equal to 3 and any other is 1. And these are the values for which the matrix A stretch vectored in a single direction.
Let's talk about characteristic polynomial. The definition is the characteristic polynomial of an n times n square metric A is the polynomial function defined by p lambda equals to determinant A minus lambda identity metric. Here is an example. As you can see, A is a 2 times 2 matrix A, B, C, D, and p lambda equals to A minus lambda times D minus lambda minus BC. And next, let's talk about properties of eigenvalue polynomial. The degree is p lambda is an nth degree polynomial. Leading coefficient is leading term is -1 n square lambda n square, and constant term p0 equals to determinant A, and roots and eigenvalues is lambda I is an eigenvalue of A if and only if p lambda I equals to 0. Here are some applications, such as pre-simple component analysis, which is PCA, characteristic polynomial of covariance matrix, eigenvalues give explained variance, and Cayley-Hamilton theorem. A matrix satisfies its own characteristic polynomial PA equals to 0. Okay, so next let's move on. Here is a question from our tutorial before. The question is find the characteristic polynomial and the eigenvalues of the following matrices: I, 3, -2, 1, and -1. So here is my answer. As you can see, A minus lambda I equals to 3 minus lambda minus 2, 1, minus 1 minus lambda equals to 3 minus lambda times -1 minus lambda minus 1 times 1. Then the answer equals to lambda squared minus 2 lambda minus 1. Then right now let it equals to 0, so we got the final answer. The first lambda 1 equals to 1 plus square root of 2, and the second lambda 2 is equals to 1 minus square root of 2. So here is the example for characteristic polynomial. As we can see, the characteristic polynomial is how we find the eigenvalues. It connects matrix algebra with polynomial equations, and it's the first step in understanding a matrix structure.
I will talk about eigenspace. In linear algebra, we often ask what does a matrix do to a vector. In most cases, it rotates or structures it in complicated ways. But surprisingly, there are certain special directions where the matrix only stretches or compresses the vector without changing its direction. These directions are captured by eigenvectors, and today we talk a step further to ask where do these eigenvectors live. This brings us to an essential concept, the eigenspace. Let's start with the formal definition. Given an multiply a matrix A, if a non-zero vector V and the scalar lambda satisfy. A multiply vector V equal lambda multiply vector V. Then vector V is called an eigenvector, and lambda is the corresponding eigenvalue. Now the eigenspace of lambda is the set of all vectors vector V that satisfy the equation, including the zero vector. Algebraically, we can rewrite this as the matrix A minus lambda times the identity matrix multiplied by vector V equals the zero vector. So the eigenspace is nothing more than the null space of the matrix A minus lambda multiply I. This reveals two key properties. The first, it is a linear subspace. It contains the zero vector and is closed under addition and the scalar multiplication. The second is dimension is called the geometric multiplicity of lambda, which tells us how many independent eigenvectors we have for that eigenvalue. Geometrically, the eigenspace represents a direction in which the transformation acts predictably, strengthening or shrinking, but not twisting. Algebraically, the size and structure of the eigenspace tell us whether a matrix is diagonalizable. If the sum of the dimension of all eigenspaces equals the size of the matrix, then we can rewrite the matrix in diagonal form, a powerful simplification in theory and computation. Eigenspace isn't just abstract theory, it powers many applications. In principle component analysis, the eigenspace of the covariance matrix identifies directions of greatest variance in data. In mechanical systems, eigenvectors describe natural models of vibration, the ways in which structures naturally move. In quantum mechanics, eigenspaces of operators represent measurable states. In network science, the eigenspace of graphs Laplacian reveals clusters and connectivity.
Conclusion: eigenvalues and eigenvectors are fundamental concepts in linear algebra. defined by the characteristic equation that A minus lambda I equals 0 and its solutions. They unlock the deeper structure of linear transformation by revealing practicable, stable directions within a system. The eigenspace, as the null space of A minus lambda I, provides a powerful framework for analysis. Crucially, these concepts transcend series, driving breakthroughs across disciplines, from PCA in data science and vibration analysis in engineering to quantum states in physics and network clustering via graph Laplacians. Understanding eigenvalues and eigenvectors is thus essential for simplifying complexity, classifying systems, and solving real-world problems, demonstrating the profound practical power of linear algebra.